Great. So what I'm going to do now is do exactly the same example problem as what you did with a single element, but the difference is I'm going to take an average body force. So this is, we're making a simplification by saying we're not going to model the body force as varying linearly across the element. We're going to make an approximation, say, or simplification, say let's compute the average body force and assume it's uniform over the element. Okay. So that is the simplification. So the rest stays exactly the same. The only thing that changes is this simplification. This is the simplification that they do in the textbook. And I want to show you what the consequence is if we do this for our single element example. Okay. So the rest, I'm not going through this again. This is exactly the same as what it's before. The only difference now is the body force is now an average, uniform, constant body force over x, not linearly varying anymore. Okay. So there's my average body force. So it's not a function of x. You can see that. So this is now my average body force that I've computed here. And then I go through the same setup, compute the stiffness matrices, integrating the stiffness matrices, computing the integrand. Yeah, this is fx. It looks exactly the same as before. The only difference is fx is now just a constant. Previously it was a linear varying function of x, which in turn was a function of psi. And now we have the integrand. We could have also just computed this with that 1616 2/3 split, because A is a constant and the body force is a constant in this case. Okay. And then we solve the system, getting the reduced system, and then solving it. Okay, that's where we are. Now we set up the solution matrix for Q with Q1, Q2, Q3, and we go through the same setup. We plot the displacements, strains, stresses, internal force. Let's look at that, and then we'll look at the work estimate. So let's first look at that. The displacement solution that we get out looks as follows. We can see essentially here 0 here. You can see the displacement looks like it's nicely tapered off there. It looks like it's flat there, so it might be that the strain is actually 0 at the end there. Let's look at that. This is how the displacement solution looks. If you look at this magnitude here, 0.0012. If you go back to the previous solution, that was 0.016. Look at that, how much higher the displacement was here at that edge, and how much lower it is here at this edge. Okay, so that's the first observation that we have. The strains are going from this value, it's 6e minus 6. Okay, that's where it starts more or less, and it ends at exactly 0. So that's observation that it's flat off. So that is at least no stress at no strain at the end there, as what we expect. And when we look at the solution here, we see that the strain is yes, significantly high, 7e minus 6. And then there's a non-zero strain at the end. Okay, so this is what we see when we look at the stress versus the exact stress. There's my stress solution, and there's the exact stress solution. And we can see here there's it really underpredicts everywhere in this case. The stress that we have is only, it's exactly at the edges for this case scenario, but everywhere in between is underpredicted. So what we expect to see is that we are going to be underpredicting our strain energy quite severely, potentially. Okay, so that is just one thing that we need to be cognizant about. We look at the internal force again, also it's underpredicting almost everywhere, only at the edges where it sort of matches the expected values, but everywhere else our stress and our internal force is underpredicting. If you look back at what we had in the previous version of the example, we were under and over predicting the stresses, so sort of getting a good estimate of what's going on, but the places where we were underpredicting was very limited in that case. Okay, so when if I were to ask you which line is a better approximation of this quadratic, if you want to fit a line through, would you choose this one, or would you say this is a better approximation? And I think everybody would say this is maybe a better approximation in terms of getting a line to try and represent the response of a quadratic. And this is so this is part of the application of using a constant body force. We get this kind of responses, and there's the internal forces. Now let's make sure everything is prepared now. Okay. Make sure so let's look at what the works look like. The work. Okay. So the estimated strain energy done by the centrifugal force in the FEM. Okay. Look at the strain energy here. 0.014 versus 0.2257. We are underpredicting the strain energy by 37%. That's significant. So our structure is seeing 37% less energy in the finite element approximation than what we would expect to see from the estimated exact solution. Okay, so that is an important thing. And if I compare it to the actual stress, the actual exact solution of the strain energy, using the exact strain, exact stress solution, we are underpredicting by 37.5. So that's essentially 38% underprediction. So the danger of not using consistent node loads is that we are loading the structures a lot less than what they actually should be loading. And that is not conservative if what you are interested in is to see if the structure would hold or not, or if you want to look at some fatigue where the strain energies are often very important. So fatigue or damage kind of calculations, this is going to be a problem. So this is all that we did is we made one simplification and look at this enormous underprediction in the response that we see. Okay, this is important to understand. Okay, so first off, we don't have to make simplifications, overly simplify the problem. We don't have to go that route. Okay, we can really model things properly, and a lot of the front-end packages would model it like this with a linear varying body force. It will be modeled as a linear varying body force. That should be fairly standard in modern eras. Okay, but if for some reason you are forcing yourself to do it this way with the simplification, and say in this course we never do the simplification unless explicitly asked to do a simplification. If we now say somebody's forcing us to do the simplification, then the question is how could we go about trying to improve the solution? And what I want to show you then in the next notebook is to say, well, one way that we can improve a finite element solution, even this solution here, is not 100%. How can we improve on the solution? And what I want to show you is in the finite element method, the way we can go about improving the solution is, for one, we could maybe up the displacement to not be quadratic, but to maybe cubic or fourth order. And then these things might be quadratics or cubic terms, as opposed to just linear. So that's one thing. So this looks almost like a nice quadratic kind of shape. You see that? If I maybe had a cubic displacement field, I would have something quadratic for the stress and for the strain. So that might be a much better prediction. So that's one way. It's more and more complex elements. And that is not really the way that typically we go for finite elements. Typically, the quadratic element is the most complex element that we'll typically use in FEM. But what we rather do is to say, let's use more elements. So what I want to show you in the next notebook is what's the implication if we go and use more elements.